तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So let us recapitulate where we ended last time. The Maxwell equations implied that you had two equations for the scalar and vector potentials, del dot A plus del squared phi equal to minus rho over epsilon naught. That is the first equation, and the second one was 1 over c squared delta phi over delta t plus del dot A. Was there a gradient of this outside? Yeah, gradient of this plus instead of del squared let me write box on A equal to on the right hand side mu naught j. Is there a plus sign or a minus sign? Plus sign, where this box is like 1 over c squared d2 minus del squared. It is the 4-dimensional analog, it is the analog in space time, as we will see when we do relativity, of the Laplacian operator. This operator, which I just call a box, is more properly called the D'Alembertian, analogous to the Laplacian, and as I said it is the wave equation, essentially the operator that governs the wave equation. So if you did not have this, it would be just the wave operator on A equal to mu naught j. These were the two equations, and then I pointed out that this set of equations is true for every pair of potentials A and phi. So the same equation is true if you had A prime, phi prime everywhere and so on, and you could choose the A and phi in such a way that del dot A was equal to 0. You could always do this, and that was gauge invariance. So in the Coulomb gauge, del dot A is equal to 0. Of course that does not uniquely fix A itself, because you could always add to this A something, once again something which satisfied del dot that new vector field equal to 0, and of course you would still be in the Coulomb gauge. So it is a family of gauges really. So in the Coulomb gauge this thing goes away, and then you are left with Poisson's equation. Now how do you solve Poisson's equation? The only point you have to remember here is that this would imply del squared phi of r comma t equal to minus rho of r t minus rho the function of r and t over epsilon naught, and there is t dependence, but then I am going to argue that this t dependence is just a spectator, because whatever t appears on the left appears on the right as well, and for this is true for every t. You could treat this t as a parameter in this equation, and really what you have to worry about is the r dependence, the fact that this is a partial derivative with respect to space variables, and that is leading to a function of r on the right hand side. Now let us go right back and see what we know from Coulomb's law for a single point charge. I know that if you have a single point charge at the origin and I ask what the potential is at any point r in space, this is a scalar function, this is the electrostatic solution we are looking at, just Coulomb's law, and what is this equal to? What is the potential at any point? It is q divided by 4 pi epsilon naught r. That is the potential due to a single point charge at the origin, right, and that is Coulomb's law. Now of course if you had many charges you would superpose the potential due to each of these charges, and that would be the answer. So once I have, for example, some charge density on the right hand side, I superpose for each of these objects, and then an equation of the form del squared phi of r is equal to rho of r divided by epsilon naught minus this kind of thing is solved by saying that phi of r at any point r is equal to an integral over all the charges that you have, and if the charge is at some point r prime, then it is rho of r prime dv prime volume element at the point r prime divided by 4 pi epsilon naught modulus r minus r prime. That is the solution. If you have a distribution of charges in space somewhere, and this is a typical point r prime, and you are asking for the potential at a point r, then all that matters is the distance between r and r prime multiplied by the volume element of charge here, that is rho of r prime dv prime integrated over all r primes over the entire extent of the charge distribution and divided by this kernel mod r minus r prime. So I know that the solution to this equation is that is the free solution, and the solution is the one that is appropriate to saying that phi of r vanishes at r equal to infinity. So boundary conditions have been put in writing that solution down, and the boundary condition that has been put in is that phi vanishes when r tends to infinity, when the distance tends to infinity. So with that boundary condition I know that this Poisson equation has that solution. Of course if you specify finite boundaries and potentials on the finite boundaries and so on, you must change the solution to Poisson's equation, but this is the free solution, and I do the same thing here. Now the fact that this is a mathematical equation which has phi of r comma t equal to rho of r comma t is completely irrelevant as far as this free solution is concerned, and it is quite clear that for every t this equation is true. So I could certainly write this right hand side, yeah, that is right.
How many boundary conditions?
Good point. The second order differential equation, how many boundary conditions do you need? Well, in the theory of partial differential equations, all second order partial differential equations have been classified, and such equations you have to specify, you have to find out first whether it is well posed or not, whether the solution exists or not, whether it is unique or not. It turns out that in this case this kind of equation is called an elliptic equation in this theory. It suffices to specify phi at all points at infinity. So really it is an infinite number of points, and what I am saying is that the boundary condition specified is that phi of r tends to 0 as mod r tends to infinity, and of course that is at spatial infinity in all directions. That is like a big boundary. So imagine the surface, all these charges are enclosed inside some finite sphere, and then you let the radius of the sphere go to infinity, impose the boundary condition that on the surface of the sphere the potential is 0, and then it is a well posed problem.
What if the boundary is finite?
Pardon me? That is what I said. If the boundary is finite, if for example somewhere you have a plate and that plate is earthed and the potential on that is 0, then that is not the solution to Poisson's equation. You have to ensure that you add extra terms to it in order to make the potential 0 at this point. But we are talking about free space, and we are talking about free boundary conditions at infinity. These are natural boundary conditions. At infinity the potential is 0. Then this is the solution, but this is only for illustration. The point I am making is that given a set of boundary conditions, appropriate set, you can solve Poisson's equation. That is all I am trying to say, and I wrote this solution down without actually trying to solve this equation. The simplest way of solving this would be to go to Fourier transforms, and then this del squared operator would just get the multiplication by k squared, and then you invert the Fourier transform and so on. since that would be a course on green functions and partial differential equations. I do not want to do that right now. Yeah.
Is there a retarded potential?
Pardon me?
Since it's an invariant of time.
Now he has brought up an interesting point, which is what I was going to do. He has anticipated me. You see, I have convinced you that if you did not have this t dependence, electrostatics, Coulomb's law we know is actually valid, and therefore that is the solution. And now I argued that for every t this is true, because t just acts as a spectator. And then let me paraphrase the question which I think is going to bother him, is bothering him, and that is the following: this potential leads to the field, because the physical field E depends on this potential. And now that rho of r prime t is over the entire charge distribution at every point in space. Suppose I have a charge distribution on the other side of the Andromeda galaxy and somebody there changes it, the potential here is affected immediately, because you see, no matter how far r prime is from r, if this potential is changed a little bit on the other side of the galaxy, then the potential here is affected immediately, and this seems to violate relativity. What would you say? Pardon me? But this is what the equations say, and that is the solution. It is easy to verify that that is the solution to this equation. Exactly. E does not depend on phi alone. E also depends on the partial derivative with respect to time of the vector potential. So remember this formula, remember that E was equal to minus delta A over delta T minus grad phi. And we have not yet solved for A. Now when you solve for A, you will discover that these A causal effects are cancelled out. So phi, this is another illustration of the fact that phi itself is not physical. It contributes, gradient of phi contributes to the electric field, but it is not the whole story. You also have this piece which you have to now solve for, and so on. So that is a good point, good observation. In any case, once that is solved, then the idea is that you put in the solution for phi here and move this to the right hand side, and del dot A was 0 in the Coulomb gauge, and then you have to solve the wave equation. And now the next question you are going to ask is, what is the solution to the wave equation? For this I have to write down the green function. Maybe we will do it later on in the course, but right now I do not want to get into this, because it is going to take me a while to write down the solution to this equation. Laplace's equation was not so bad, Poisson's equation, because you already know Coulomb's law, and I just convinced you that that is the solution, that is it. But this is going to take a little more doing, solving an equation of this kind. It is not an elliptic partial differential equation, this is called a hyperbolic partial differential equation. This minus sign here is very crucial, and things are a little messier, but you have to take it from me as an article of faith that there is a well defined technique to solve this equation as well, and the problem is solved in principle. Okay, now yeah.
But Maxwell's equation phi is not electrostatic potential.
No, it is not phi, phi is the scalar potential. Phi is the scalar. Pardon me?
What are you trying to do with this electrostatic potential?
No, I said let us go back, instead of solving Laplace Poisson's equation here ab initio, I said let us go back and recall our knowledge of Coulomb's law and electrostatics, where I switch off all the time dependencies and I just have del squared phi equal to rho of r minus rho of r, and I said I know the solution, I know Coulomb's law. I put that down, and then by superposition that integral turned out to be the solution, and then I said t is just a parameter in the exact equation here in the general case, and I just put that down there. So that was just to show you that the solution can be written down, okay. And in this case I am not even doing that, I am just saying the solution can be written down, okay. We will not do that at the moment, right. So in the Coulomb gauge we know in principle how to solve the Maxwell equations. There is the other gauge which is the Lorentz gauge. In that Lorentz gauge this combination is 0, and then you start by writing down the solution to the wave equation for with J as a source term for the vector potential, put that in here, this will no longer be 0 here, and then del squared phi equal to a given function rho plus a known function, and therefore once again you solve Poisson's equation and the problem is solved in principle completely. Now this is not my primary concern, we will come back to this when we do relativity, because we would like to find out what is the meaning of this gauge, and I might as well say it here right now. It turns out that this quantity, this set of quantities phi over c and a together form what is called a 4 vector, a 4-dimensional vector, just as a vector that you are used to in 3 dimensions is defined as a quantity, a set of 3 quantities which transforms exactly like the coordinates themselves do under rotations of the coordinate axes. In exactly the same way, this set of 4 quantities will transform like the space time coordinates do, like time and the 3 space coordinates do under Lorentz transformations, and then this would be called a Lorentz vector or a 4 vector. So this combination itself has a specific transformation property, just as Ct and R have a specific transformation property under Lorentz transformations. I put a C here because I would like to have all the components of a given vector to have the same physical dimensions, and once I multiply t by a velocity, a fundamental velocity, this has dimensions of length. So this length and those 3 lengths here x, y, z transform under Lorentz transformations by the rules of Lorentz transformations, and my assertion is that this set of quantities transforms in exactly the same way. They form the 4 components of a 4 vector, the time-like component and the 3 spatial components. But you can find other such combinations, for example C rho and J itself. So it turns out that the charge density multiplied by C and the current density have exactly the same physical dimensions, and that combination also transforms like a 4-dimensional vector. So that is the reason why electromagnetism looks so complicated when you write it in terms of 3-dimensional vectors, as we have done here. Once you write it in the 4 vector language, it is very simple, it is very straightforward, and the equations are very elegant indeed. You could also ask what the gradient operator is, what is the analog of the gradient operator in 4 dimensions, and just as we had a D'Alembert operator here, one would like to define 1 over c delta over delta t, and of course the del operator, but for a reason which will become clear later, it is minus the del operator. This quantity would transform like a 4-dimensional vector, that is the appropriate 4-dimensional divergence, 4-dimensional del operator. And it is not hard to see that if you take that del operator and dot it with itself, you would get this operator here, and with the dot product has to be defined in a specific manner, which we will do when we do relativity. So the point I want to make is that this combination here turns out to be the 4-dimensional divergence of this 4-dimensional vector, and it would be written in the form del mu a mu, where mu runs over the values, this index runs over the values 0, 1, 2, 3, 0 for time, 1, 2, 3 for the space variables, and therefore setting this equal to 0 is equivalent to setting this equal to 0, and this is a scalar. So this means under Lorentz transformations the numerical value of this quantity is the same in all frames of reference, all inertial frames. Therefore once you set it equal to 0 in one frame, it is 0 in all frames. In other words, once you are in the Lorentz gauge in one inertial frame, you are also in the Lorentz gauge in all inertial frames. That is the great advantage of the Lorentz gauge. That advantage is lost here because del dot A does not remain unchanged when you go to another inertial frame, it changes from frame to frame. So if it is 0 in one frame, it is non-zero in other inertial frames, and you can make it 0 once again by making a subsequent gauge transformation, but it could get tedious. So depending on the problem that you have, you choose either the Lorentz gauge or the Coulomb gauge or any other gauge, find your own gauge and solve your own problems. So it is infinite amount of freedom that is available. You have to have observe some rules, but otherwise the choice of gauge is extremely useful, and you saw here how useful it was. But I emphasize once again that physical quantities, measurable quantities in classical electromagnetism would depend on the fields, on E and B. If they depend on A and phi, you must make sure that they do not change under gauge transformations. So that is important, as we saw. So you can use this freedom quite a lot, but then the field should not change under this. And indeed, if you recall, what the energy density of the electromagnetic field is. It is epsilon naught E squared plus 1 over mu naught B squared multiplied by half, and it does not depend on A and phi directly, it depends on E and B, and that does not change. Similarly, the Poynting vector, which tells you the momentum density, is E cross B apart from some constant, and again depends only on the physical fields. So this is important to remember, and with this let us do the following. Let us go back and ask what could possibly be the Lagrangian for a charged particle in an electromagnetic field. I am going to write the Lagrangian down and then explain where it came from. So let me first write it down. I just assert that this is a Lagrangian, and later we will justify. I will justify it post facto based on invariance considerations. So for a charged particle in an electromagnetic field, the L for the particle, and for the moment I am focused only on the particle. I am not worried about the field. The field is applied from outside, could change with space and time, but I am interested in the equation of motion of the particle. So what can the Lagrangian depend on? It depends on the coordinates of the particle and the velocity of the particle, q and q dot, but instead of q I really have the 3 coordinates L, R, and the velocity is v. It could depend on time explicitly, because the fields that I apply could change with time. I could switch on an alternating current or something like that, an alternating voltage, in which case I must include this T explicitly, and this is equal to again the kinetic energy 1/2 mv squared, and it is not T minus v, and the reason is the magnetic field produces a force which is velocity dependent, q v cross b, and this is not within the purview of the normal T minus v kind of thing, slightly different, and I write the Lagrangian down and we will see where it leads us. And this Lagrangian is q, this is the charge on the particle, so charge q mass m, and the particle is assumed to be non-relativistic, so this entire formalism is valid non-relativistically. So even though the fields would obey Maxwell's equations, which have the speed of light buried in them, the particle itself is assumed to move always at a speed much slower than the speed of light. That is an assumption. Of course you could write it down in the relativistic case, but we would do that after we study relativity, okay, plus q times a dot v minus q times phi. That happens to be the Lagrangian for a charged particle in an electromagnetic field, a very strange combination of this kind. Now let me try post facto to justify it slowly where it comes from. The Lagrangian is a scalar, as was pointed out, so all terms on this are scalars. We are trying to describe the interaction of the particle, charged particle, with the applied field. So it is reasonable that there is some property of the charged particle and some property of the field getting coupled to each other. This is the charge and that is the potential, scalar potential. Q times V is the current due to this charge, and the current is getting dotted with the vector potential. You can already see this is looking like, starting to look like a dot product of some property of the particle and a dot product of some property with some property of the field, and indeed if you recall that J mu is C rho and J, current density, and the vector potential A mu is phi over C A, the 4-dimensional analog of the current density, the 4-dimensional analog of the vector potential here, the 4 vector potential, then this combination here is nothing but J mu A mu. It is the 4-dimensional dot product of the current with the vector potential. That is the reason for this Lagrangian. But again, at the moment you have to take this Lagrangian from me as a matter of a given quantity, and later we will justify it a little more, but I thought I should mention this here as to where this comes from, what is the rationale behind it, and later on we will justify it more rigorously. Okay. So here is the Lagrangian, but this is not a very simple Lagrangian, because this quantity could depend on space and time, it could change, and similarly here plus q a of r comma t dot v. And remember, r is the coordinate of the particle and v is the instantaneous velocity of the particle, and this is the Lagrangian. Now what is the set of equations of motion? Well, the Euler-Lagrange equations say delta L over delta each coordinate x, y, z, etc., delta L over delta x must be equal to d over dt delta L over delta x dot. X dot is v sub x by definition, the x component of the velocity, and similarly for the y and z coordinates. So you have 3 equations of motion for each. Yes.
How are we sure that it's d by dt rather than dou by dou t? How are we sure that dou L by dou x dot doesn't depend on time?
It would depend on time. That's, yeah, it does depend on time.
Depend on other coordinates.
It does depend on other coordinates. That's why it's a total derivative. That's the whole point. This is a total derivative. It's not differentiating just the partial derivative. In fact, if you didn't have time dependence in the Lagrangian, if you had an autonomous system, then this thing here would be 0 if you had a partial derivative. That is not true. It is a total derivative, absolutely. It is very important, it is a good observation. It is the total derivative with respect to time. So if the coordinates change with time, then you have to differentiate. The time derivative would be non-zero. It is crucial. It is the total derivative. Now let us see what where this gives us, and so on, and similarly for y and z. I could use the index notation and do this, but let us just do this with x, y, z, so it becomes familiar, it looks familiar, and let us compute what is delta L over delta x dot equal to. What is this going to be? Well, there is going to be a derivative here because it is half m vx squared, and if you differentiate it you get mx dot, that is from this point here. Remember, vy, vz are independent of vx as dynamical variables, so you differentiate with respect to vx alone and you differentiate only half m vx squared here, which produces a factor 2, cancels this and gives you that. But there is also dependence here, and this is ax vx, and if you differentiate it you get plus q ax. I will suppress the r and t dependence inside, it is understood sitting there. And what is delta L over delta x equal to? There is nothing from here because these are velocities, but there is dependence in here on x, y as well as z of every component. So if I write that down, you get q delta ax over delta x vx plus delta ay over delta x vy plus delta az over delta x vz. That is this term here if I differentiate with respect to x, and then there is derivatives here, so you can't forget that. So it is minus q delta phi over delta x. And now we plug it into the Euler-Lagrange equation, and it says this quantity is equal to, on this side, the time derivative of this, the total time derivative. So that is equal to mx double dot plus q dax over dt, total derivative. And this is the equation of motion. So now permit me to erase this part and then rewrite it, and you get mass times the acceleration mx double dot equal to, or let us write it as m dvx over dt equal to, move this to the right hand side and let us see what happens. So you have minus q dax over dt, but that can be written as minus q delta ax over delta t, and then delta Ax over delta x dx over dt and so on. But let us bring that last term here first. So that is minus q delta phi over delta x. So that takes care of the last term, and then I have to keep track of all the other terms. So plus q times delta Ax over delta Vx, sorry, delta x Vx plus delta A y over delta x Vy plus delta Az over delta x Vz minus the terms that were left out from here, the spatial derivatives, and the first of these was delta Ax over delta x dx over dt, that is Vx itself, minus delta Ax over delta y dy over dt, that is Vy, and minus delta Ax over delta z Vz. So that is the full set of terms. Painful doing it component, easier to do it with index notation, but this should illustrate what is going on, and of course this term cancels. And then you begin to see what is going on. This is equal to minus q, or rather plus q. What is minus delta Ax over delta t minus delta phi over delta x? Remember that E was equal to minus delta A over delta t minus grad phi. So the x component of E is minus delta Ax over delta t minus the x component of the grad of phi, which is minus delta phi over delta x. So you see this has immediately emerged. This is q times E sub x, it has immediately emerged, plus q times, and now let us take terms together. So let us take the Vy terms here, and you have Vy times delta Ay over delta x minus delta Ax over delta y. Minus Vz times delta z minus delta Az over delta x. So that takes care of these two terms here. But what is this equal to? Well, remember B equal to curl A, L cross A. So Bz is equal to delta over delta x Ay minus delta over delta y Ax in cyclic order of 1, 2, 3. So this quantity is equal to Bz, and similarly this quantity equal to By. So therefore this says this is equal to q Ex plus Vy Bz minus Vz By, that is equal to V cross B, the x component of it. So it says the x component of m dV vector over dt is the x component of QE plus the x component of q times V cross B, and now it is true for every component because I chose the x component arbitrarily, and it is true component by component. So this immediately tells you that the equation of motion is m dV over dt equal to q E plus B cross B as vectors. This is the Lorentz force. So the Lagrangian has given us the correct equation of motion. We worked backwards. I mean, I shamelessly wrote this Lagrangian down in order to produce the right equation of motion, but this is the way it is derived, and as I pointed out, the Lagrangian itself is obtained by invariance considerations. So there is something fundamental about the whole thing. The fact that the 4-dimensional dot product of the current with the vector potential is the Lagrangian, it is called minimal coupling, it is the least you can do, and it has been experimentally verified to incredible accuracy, 10 decimal places or something like that in quantum electrodynamics. So we know this is true and we have good reason to believe that this is exact, but the fact is that we work backwards. We really said we have the Lorentz force as an experimental observation, and what is the Lagrangian that gives it? Well, that complicated velocity dependent Lagrangian happens to give it. But now if you are perceptive, you should ask the obvious question. I wrote this Lagrangian down, and that is a very, very deep point. Remember that the Lagrangian I wrote down was 1/2 m v squared plus q a dot v minus q phi. Two questions arise. You could ask, what about the electromagnetic field itself? That could change, and it should also come from some Lagrangian. I should write a Lagrangian density for the electromagnetic field. Yes, indeed you can, but we are not finding the equations of motion of the electromagnetic field. We assume we know them already. What are they? Maxwell equations, the Maxwell equations. So I have not derived the Maxwell equations from a Lagrangian density. That is a little more complicated exercise. It requires classical field theory. We have not done that, but the fact is, for the particle, non-relativistic particle, this is the Lagrangian. Does something strike you funny about this Lagrangian? Does it make you uneasy a little bit? Pardon me? It depends on the auxiliary variables. It depends on a and phi. It does not seem to depend on E and B directly, and yet we are producing a physical equation here. Please note the equation here is in terms of E and B. These are physical quantities, measurable quantities on both sides. We started with these auxiliary quantities which are not unique, so it should bother you that the Lagrangian is not unique, not in the trivial sense of adding a constant which does not get differentiated, but serious non-uniqueness, because it is in terms of a and phi, which I can change by gauge transformations. And the question is, how are we sure that this is going to remain as it is eventually? Well, the answer of course is trivial, because if I put any other a and phi, exactly the same thing would happen, because E and B are gauge invariant quantities, and we know that under gauge transformations E and B do not change. So just as B is curl A, B is also curl A prime, and E is minus delta A over delta T minus grad phi, also minus delta A prime over delta T minus grad phi prime. So it does not matter. On the other hand, you could ask, what happens to the Lagrangian itself if I make a gauge transformation? Now that is a serious question. So what happens to this L? And this leads us to the non-uniqueness of the Lagrangian. Under a gauge transformation, L goes to L prime is equal to 1/2 mv squared plus q a prime dot v minus q phi prime, where a prime is related to a by addition of a gradient of chi. So this is equal to 1/2 mv squared plus q a dot v minus q phi plus q grad chi dot v, because that is a prime, plus q delta chi over delta t, because phi prime was phi minus delta chi over delta t, and this is the extra piece in the Lagrangian. So this is equal to 1/2 equal to L, the original L, plus this quantity here. Now what does one make of it? Well, please look at it and see, remember, realize that it is equal to q times d over dt of chi, because the total derivative of chi, which is a function by the way of r and t in general as we know, is equal to delta chi over delta t plus delta chi over delta x dx over dt and so on, and that is just this. I mean, I have written this simple thing down, that d over dt of a scalar function is plus v dot del. When you act on a scalar function on the right hand side, this is exactly what you get, and you are familiar with the second term in fluid dynamics. It is called the convective derivative. So the total time derivative is the partial derivative with respect to time plus the convective derivative. that is exactly, it is just a rule of calculus here. Well, let us take this q in and write it as d over dt of q chi. So the lesson we have learnt here is that if you make a gauge transformation, the Lorentz force equation will not change, it is in terms of physical quantities, but the Lagrangian changes by the total derivative of a function of the coordinates and time in general. That does not change your equations of motion. This is a general statement, not restricted to electromagnetic fields or anything like that. In general, the Lagrangian is non-unique to the extent that you can add to it an arbitrary total time derivative of an arbitrary function of the coordinates and time. That is true for any system, and if you go back here and look at how we found the equations of motion, it will become obvious. We started by saying I define an action t1 t2 equal to integral t1 to t2 L dt, and L was a function of q, q dot and t in general. I go back to the notation q for the coordinate, I did not want to use it here because I used it for the charge. Okay. And now if I write A prime is t1 to t2 L prime dt, this is equal to the original A plus an integral t1 to t2 df of the q's and t dt. So the original Lagrangian, to that if I add a df over dt, I get L prime is L plus df over dt for an arbitrary function of the coordinates and time, and that is what A prime becomes. And the equations of motion, the Euler-Lagrange equations, were found by varying A and claiming that the first order variation is 0, the principle of extremal action. So I varied it between time t1 and time t2 by any path whatsoever, no variation of the q's at these points, delta q was 0 here and 0 here. But then what does this give you? This is equal to A plus f of q of t1 t2 rather minus f q t1 t1. I can integrate this out precisely because it is a total derivative term, and then it is the 2 points at the ends. And now our variation to derive the equations of motion permit all possible variations inside with the end points kept fixed, and at the end points there is no delta q, and since this extra piece depends only on the q's at the end points, these two terms do not contribute to the variation at all. Therefore the equations of motion do not change. Now of course you should ask, what kind of transformation is this? What does this mean? What kind of transformation is this? It will turn out, I will explain this as we go along, it will turn out that this electromagnetic example is a very, very useful one because it is very instructive. It tells us what is going on in the general case. Well, it was a gauge transformation here, so I could in some sense continue to call that a gauge transformation. By that I mean, to the Lagrangian of a system I add the total time derivative of an arbitrary function of the coordinates and time, and the equations do not change. Not velocities also, please notice I have not allowed for you to add a function of the q dots here. This could be done, but then I have to start putting conditions on this f, but without any conditions this is the general case. It has got profound implications because when we do the Hamiltonian framework, it will turn out that this same freedom of adding to the Lagrangian the total derivative of such a function would be called a canonical transformation in Hamiltonian mechanics. So there is a close link between what goes on here and what we are going to study a little later, and then it will become much more natural in that framework, but already you can see that the Lagrangian is not unique. You can add a total derivative, and in the electromagnetic case, in this case physically a gauge transformation is equivalent to adding the total time derivative of an arbitrary gauge function to the Lagrangian. It does not change the equations of motion. That is a lesson worth keeping in mind. Yeah. Is there some way we could have expected this? Well, you can put a q dot, but you will have to put further conditions on it. It would have to be a suitable symmetric function and so on, but not getting into that right now. But this is the simplest case, yes. Okay. I am not sure if I have answered your question. Yeah. Yeah, so in this language it is obvious, right. I mean it's in this language, once I say there is no variation here, it is quite clear you can add something which depends only on these endpoints and then the equations will not change. So in that sense we could have predicted this, but it is going to have physical implications. The implication of that in this context was precisely gauge transformations, but that could come about from other transformations as well. So we are going to look at that. There could be other symmetry transformations on the Lagrangian which would leave the equations of motion unchanged, and the necessary condition for that would be that the Lagrangian should change only by the total time derivative of a function. Okay. So it will get linked to various other quantities, as we will see. We will get back to this thing here. Okay. This brings me, yeah.
So does Lagrangian exist for every dynamical system?
No, no, I am looking at only that class of dynamical systems for which you can write down Lagrangians, for which the equations of motion arise as Euler-Lagrange equations. So that is a restricted class of dynamical systems. So in between I also went and did general dynamical systems for which you can't write any Lagrangian or anything down. So you can push that to some extent, but once you have a Lagrangian structure you can push things much more. So certainly not all dynamical systems. This brings me to a very important observation, and that will take us back to general dynamical systems, and that is the following. When I wrote the Euler-Lagrange equations down, let us rewrite this thing. So I have an L of q dot and t, and from this I had equations of the form delta L over delta qi equal to d over dt delta L over delta qi dot, and I was equal to 1, 2. We looked at systems with a finite number of degrees of freedom, n of them. So these were the Euler-Lagrange equations. And now one of the most crucial things in solving general dynamical equations is to find a constant of the motion. The moment you find a constant of the motion, as we saw in the case of the harmonic oscillator, we had just the energy as the constant of the motion, and immediately that gave us the phase trajectory as ellipses. So the important lesson is, every time you have a constant of the motion you have solved part of the problem. You would like to find more and more constants of the motion. Now in this problem the phase space is 2n dimensional, and the trajectory is a 2n dimensional, is a line in this 2n dimensional space. It is like a piece of thread moving around in this 2n dimensional space. To specify this line in a 2n dimensional space, how many constants of the motion should I have? I should have 2n minus 1, because if I have one constant of the motion, some function of the q dots equal to constant, that gives me a surface of 2n minus 1 dimensions. If I have another independent constant of the motion, another 2n minus 1 dimensional surface. The mutual intersection of these is generically 2n minus 2 dimensional. Just as in ordinary 3 dimensions, I have a sphere, surface of a sphere, that is 2 dimensional. I have a plane that is 2 dimensional. These two cut each other and the result is a circle in general, which is 1 dimensional. So every time you have two surfaces intersect, the dimensionality of the intersection is lowered. Now you want to go from 2n dimensional phase space to a 1 dimensional object, you need to have 2n minus 1 constants of the motion. So every time you have a constant of the motion you solve the problem a little bit, and sometimes you can use, and they are going to be closely linked to symmetries, and that is one of the things I want to emphasize in this course. We would like to find constants of the motion. This is very important. In fact, in a sense all dynamical systems of this kind are governed by their constants of the motion. Once you have done that, the job is done. One of the things that happens in Lagrangian mechanics is that sometimes you may have a situation where the Lagrangian does not depend on a coordinate, on a particular coordinate. Such a coordinate is called a cyclic coordinate, for reasons I will not go into right now. So if L is independent of a particular Qj, let us say, so I avoid confusion with I, some particular Qj, then Qj is an ignorable or cyclic coordinate. What does that imply at once from this equation? This would imply d over dt delta L over delta Qj dot equal to 0, but that equation is solved immediately. And what does that imply? I am going to use the COM for constant of the motion. So it says delta L over delta Q dot, that particular Q dot is a constant of the motion, does not change. Its numerical value would be the same for all, for a given initial condition, would remain constant in time. The numerical value would depend on the initial conditions, but once you have specified that, it remains exactly the same. Therefore, a very important thing is to find cyclic coordinates, because then you find constants of the motion, and every time you do that, you won the battle a little more, you have gone a little further. Let us look at motion of a particle in a plane in 2 dimensions, and let us assume, for example, that the force the particle sees is a conservative force, and that the force is always directed to the center of the attraction or the repulsion, a central force. What would the kinetic energy look like? So I have motion of a particle in a plane, and these are the x and y axes, and I look at polar coordinates, plane polar coordinates. Rho and phi. This is the square root of x squared plus y squared, and that is tan inverse y over x. I use this rather than r and theta because I want to reserve that for spherical polar coordinates. The Lagrangian of this particle is a function of the coordinates x, y, x dot, y dot, but I could also write it in terms of rho phi, rho dot, phi dot, and let us assume that it is a constant potential in the sense that it is time independent and always acts in a central fashion. It is a function only of the distance from the origin of rho. So this is equal to the kinetic energy half times m times Vx squared plus Vy squared, but I should write this in plane polar coordinates. What is V squared in plane polar coordinates? Rho dot squared, because there is a radial velocity, rho dot squared plus rho squared phi dot squared, that is the kinetic energy, minus the potential energy V, but now I am going to say this is a function of rho alone, central potential, like this. Is there a cyclic coordinate? Phi is a cyclic coordinate. Immediately it follows that phi is a cyclic coordinate. So you are absolutely guaranteed phi is a cyclic coordinate. And that implies that delta L over delta phi dot is a constant of the motion. And what is delta L over delta phi dot? We are coming to that, yeah, it is angular momentum. So if I differentiate it here, I get a phi dot here, and if I differentiate, the 2 goes away, so it is equal to m rho squared phi dot. And of course you recognize that this is the moment of inertia of the particle about the origin, and that is the angular speed, angular velocity. So this is equal to the angular momentum of the particle about the origin, and we are guaranteed it is constant. Of course we know that in the central force there is no torque, and therefore the angular momentum is constant, but it is nice to see that it comes out automatically as a trivial statement. Phi is a cyclic coordinate, so the angular momentum is constant. Incidentally, let me call this in anticipation of the notation P sub phi to show that it is the momentum conjugate to phi. I am going to use this word conjugate repeatedly and explain what it means, but let us anticipate this a little bit. So it says this is a constant of the motion. That is a big help, that is a big help. In this problem, how many degrees of freedom are there? 2. What is the dimensionality of the phase space? 4. Now you would like this problem to be solvable. How many constants of the motion do you need? You need 3. How many do you have? We found 1, but we also know in the back of our minds that the total energy is going to be constant. Actually the Hamiltonian is going to be constant. So we have a second one and we need one more. We need one more. That is not always easy to find in this problem, but let me anticipate things again by saying that in problems of this kind, if you have a 2n dimensional phase space, sometimes if you have n constants of the motion, that is enough. You can find the rest. They are called integrable, but I am jumping ahead a little bit, but this is an example of such a system. These two are enough, these two are enough. They are independent. The angular momentum and the total energy are independent of each other. You can specify each of them independently, and therefore this problem is in some sense solvable. Let us do the same thing for 3-dimensional motion and look at what happens. In 3 dimensions I have to use spherical polar coordinates, and I am again going to assume why do I always put x here, y there and z there? I could have done it the other way. Why do I do that? Pardon me? Well, why don't I choose x on the right hand side and y outside the board and put z up there? Yeah, I would like to choose a right handed coordinate system, right. I would like to choose a right, just no special reason, but I would like to make sure that when I twist from x to y I go upwards. This, okay. I mean there is no special reason, it is left handed coordinate systems are just as good, and this is it reminds me of this famous TV scene about George Bush, because every time in class I explain right handed coordinates I always use the left hand because the right hand is chalk and I say this, but then George Bush does this when he says, well, the right hand does not know what the left hand is doing. This is a very, very famous scene. Okay, so here we are going to have L of r theta phi r dot theta dot phi dot, and that is equal to 1/2 m, and now there is an r dot squared plus r squared theta dot squared plus r squared sine squared theta phi dot squared minus v of r alone. That is a central potential. Is there a cyclic coordinate? Yes, it is a cyclic coordinate. So once again the azimuthal angle phi is a cyclic coordinate. This implies that the derivative with respect to phi dot is a constant, so it implies that m r squared sine squared theta phi dot equal to p phi equal to a constant of the motion. Again, what is that quantity? It is in fact the angular momentum, but in 3 dimensions angular momentum has 3 components, unlike in 2 dimensions where it has just 1 component. In 3 dimensions angular momentum has 3 components, and therefore this is just one component, the azimuthal component of the angular momentum, and buried here, although we do not see it as cyclic coordinates, there are other constants of the motion. There is actually the total angular momentum, that too is a constant, but that is going to involve theta, it is going to involve other combinations as well. So this is just one component, and in this problem, by the way, how many constants of the motion do you need to solve this problem? You need 5, but like I said, these are systems where 3 would do. You have the total energy, the Hamiltonian, you have this p phi, and you need one more to solve it, and it will turn out to be the square of the total angular momentum. Now once you have that, the problem is solved. Incidentally, that is the reason why when you go to quantum mechanics, the hydrogen atom is specified by a principal quantum number, an orbital angular momentum quantum number, and a magnetic quantum number, because constants of the motion translate into quantum numbers in quantum mechanics. This is the connection between these two, which we will see. So once again I will stop here. We see that the existence of cyclic coordinates is extremely helpful. We discovered the cyclic coordinate here by changing to spherical polar coordinates. Had we looked at it in Cartesian coordinates, this would not have been apparent. So you begin to see also the advantage of using symmetry to choose coordinate systems appropriately. So let me stop here, and then we take it up from this point, and once we are ready to do the Hamiltonian framework.